Ladies and gentlemen, welcome to the second talk of this session. The speaker is Laurentiu Rodina from BIMSA. He is an expert in QFT and scattering amplitudes and is going to talk on emergence of locality and unitarity from hidden zeros for the next hour. Please join me in welcoming Laurentiu Rodina.
Okay, is this? Yeah, okay, it's working. Hey, yeah, it's great to be here, and it's even greater to see people come here to visit us at BIMSA. So today I'll talk about some sort of project that I've been focused on for more than 10 years now, and it's evolved in different ways. And then it took a break, and now recently with some new technology that appeared, some new progress can be made, and I'll talk about this. So other people already motivated why you need to do, why scattering amplitudes are important. And this is my very short slide on various things why scattering amplitudes are important. Of course, they're just a fundamental object in QFT, and if you're interested in QFT, it's an object that you should know how to compute and understand what it tells you. It encodes particle spectra and interactions, and of course, that's why it's relevant to experiments and people trying to figure out the standard model. But besides just the fact that it's some other object in QFT that you can compute, it has some special properties that other objects don't have. So one specific example is this double copy relation, which I won't talk about, but it's a very strange relation that people found between gauge theory and gravity. And this relation hints at new ways to define perturbative quantum gravity. And for example, people are looking that why n equals 8 supergravity could be UV finite, which would be a concrete example of a pure QFT theory that's UV finite, right? Which would be pretty important. I mentioned already it's obviously important for experiments. So people computing amplitudes have the actual purpose to give these results to experimentalists who use them in collider physics. Very recently, methods from scattering amplitudes are being used in gravitational waves, and perhaps in the future, even for cosmological correlators, and who knows what else. Okay, for the more mathematically oriented people, and we have lots of them in the amplitudes community, amplitude research just connects and even inspires some pure mathematics, ranging from algebraic geometry to combinatorics and many others. Okay, so even if you're just a pure mathematician who doesn't care about physics, there's plenty of things to discover in amplitudes and use it in who knows what other directions. Yes? I will in a minute. Most of the talk is basically more combinatorics than physics, so you'll see. And so the direction I'm sort of more motivated by, besides all of these things which are obviously important, but honestly, I mean, we always say that what we do is relevant experimentally. I've never spoken to an experimentalist in my life, but of course, I believe what I do could be useful to one someday. But I'm more interested in the new structures that you find in physics by looking at scattering amplitudes. So there's something, I would say, magical about scattering amplitudes, which is that if you look at these amplitudes, and I'll describe this in more detail, you find some new simplicity and hidden symmetries, which seem to suggest that there are deeper principles that we don't know about, that go very well beyond Feynman diagrams and the usual principles that we use, like unitarity, locality. And some people hope that scattering amplitudes can also tell us how we can move beyond space-time. Of course, this is very ambitious. And in this talk, I'll actually want to understand how unitarity and locality can be even viewed as emergent in some specific contexts. Of course, why this is important is not just as a toy example, but obviously, if you want to move beyond space-time and derive a theory of quantum gravity, there are various problems with locality and unitarity, as we know. So there's various motivations. By a complete theory, beyond QFT, these principles won't be fundamental, right? They'll emerge from something else. And if that's true, then we really need to understand this even in the simplistic possible examples, right? So we cannot hope that the theory of everything will not be local or unitary. It will have some crazy ideas if we don't understand how these things emerge in the simplest examples in QFT, right? So this is a good starting point. Okay, so why study scattering amplitudes in this context? Well, there's something that I view as a very unreasonable and unusual generosity of scattering amplitudes. So they're at an interesting point that they're simple enough to compute in some cases, but they're still highly non-trivial and also useful, of course, for practical purposes, and also very, very rich, right? So they're not simple enough to be just trivial objects that we could have understood 50 years ago. They're sort of complicated, but they're still simple enough that you can make progress from very different directions, okay? And understand all of this structure. And for some reason that I don't really understand, and I don't think anybody understands, is that scattering amplitudes seem to reveal secrets that go beyond this formalism that we apply to compute them, right? And in the last decade or 2 decades or so, it's become apparent that the usual traditional Lagrangian and Feynman diagrams are just terrible to compute amplitudes. But somehow, in the end, the amplitudes survive all of these cruel procedures that we apply and still survive in a nice object that hints towards a direction to go beyond QFT and beyond these methods that are just not the right tools to compute amplitudes. So I sort of view them as an advanced alien object that was given to us. And it contains the secrets of the universe, but we don't know how to get into it. So we're just probing and understanding various bits and pieces. Okay, so that's my view. Maybe it's delusional, but that's sort of the way I understand it. And of course, other people might have their favorite alien object within QFT, but this is the one I'm interested in. So like I said, in this talk, I'll focus on how you can get unitarity and locality, which normally we consider to be fundamental principles in quantum field theory, how they can emerge from other properties. Okay? In some concrete contexts, and I'll do this at both 3 and 1 loop. Okay? So I'm not saying that in all of QFT unitarity follows from something else, although that would be nice to eventually find. But in some concrete contexts, for some concrete amplitudes, this happens. Okay? And this is what I'll describe. So the big and practical question in this field is exactly what determines an amplitude. Right, so in recent years, there's been various methods to compute amplitudes, from very crazy geometrical ideas to more efficient recursions or other things like this. But there's a very simple question you can always ask. How do you know an amplitude is correct? Right, say you give this as a homework to your graduate student, compute some 5-point Yang-Mills amplitude, he gives you the answer. How do you know it's correct? Well, obviously, like Marcus said, you can check it numerically a few times and then probably assume it is correct. Of course, that's not a proof in any sense. So one can ask a very rigorous mathematical question. What is the minimal data needed to fix an amplitude? Okay? And try to prove this thing. Because usually what people do is they have this amplitude, maybe they invent a new formula for an amplitude. And then they say, okay, let's check for the consistency. Is it local? Is it unitary? Does it satisfy gauge invariance, soft terms, recursion, and so on? But this is still not the proof. Okay, this is still just some random checks that sort of give you some confidence. But I want to get a proof in some way. Okay, and so this is what I've been focused on for many years now. And the surprise that shows up is that all of these principles often form an overdetermined system. Okay, so you don't need all of this information to fix amplitudes. So this tells you that not all of these principles are independent. Okay, and it turns out that what you think are the most fundamental, like locality and unitarity, are actually the ones that are the least constraining compared to everything else. Okay, so this is a math institute, so I should have some definitions, because it happens many times. I give a talk on scattering amplitudes, and at the end, the mathematician says, okay, so what's a scattering amplitude? So this is what a scattering amplitude is formally. It's a distribution valued operator acting on the space of asymptotic states. So you give it some in states, some particles, and out goes, you get some out states. And then this function computes the probability for this event to occur. Okay, so this is the physics picture. You just send in some stuff together, and you'll get some probability that these things interact. And that's what this amplitude tells you. Okay, and this amplitude satisfies various properties: unitarity, Lorentz invariance, analyticity, which could be taken to be the same as locality in some sense, crossing symmetry, and a few others. Okay, And traditionally, this is computed from Lagrangians via Feynman rules, at least when we know what the theory is. Okay, so you can make lots of progress even when you have no idea what theory you're looking at. If you just know these principles, you can still sort of do something that's called the analytic S-matrix bootstrap and still get very important constraints on quantum gravity and theories in general, even when you don't know what the theory is, so you don't know what to compute. Okay, so in practice, how do you compute scattering amplitudes? Just so, because there might be people who haven't computed a scattering amplitude ever. So this is the basic stuff that you have to do. You start with a Lagrangian that defines your theory, and usually you'll have a kinetic term that tells you the propagator, and you'll have some interaction term. From this Lagrangian, you extract the Feynman rules, and then you get the Feynman diagrams, you add them all together, and that gives you scattering amplitude. Okay, so in the simplest possible theory, which is this one, phi cubed theory, this is the 4-point amplitude, given just by these some of these diagrams, where you have a propagator that gives you the piece here, the pole, singularity. Then you have the vertices come from here, which goes into numerator. Okay, this is 4 points and then 5 points and so on. Okay, so in principle, you can compute all of these things, including a tree level, loop level. So in theory, we know how to compute any amplitude where we know the theory, right? That's not the problem. And so to clarify what I mean by these principles, since especially locality can have different definitions depending on who you ask, I mean by locality, which physically means something like interactions are point-like in space-time. In amplitude language, locality, I take it to be that the pole structure corresponds to propagators. So for example, you can see this sort of pole structure corresponds to these two propagators. So you take the incoming momenta and you add them one at a time. If you had something like a higher power of a pole here, or some crazy combination of momenta that doesn't correspond to a diagram, I would call that to be non-local. Okay? And then by unitarity, which physically means something like probabilities of all possible events to happen is 1. In amplitude language, it means that the amplitude factorizes on these poles. Okay? So for example, if I take this 5-point amplitude, I go on the residue on this pole, I'll get something that looks like this. It's going to be lower point amplitudes. Okay? So this is the statement of unitarity. Also, we can call it factorization when you talk about amplitudes. Okay, so like I said, we can do that in general. We can compute all of the amplitudes. Here's the Yang-Mills 5-point amplitude. You can just do it using the same rules, okay? Maybe a 5.1 is too difficult for a homework exercise, but a 4.1 can be done. You can see it's quite large. This is what one of these terms looks like. It's the E are the polarization vectors, and these are the momenta of the 5 gluons. It's a very complicated function. But in the right variables, it simplifies dramatically. And this is something that Johannes talked about in his talk. And some variables that I won't describe, but there's just some simple definition for what this bracket means in terms of these variables. All of this thing collapses to this, which is known as the Park-Taylor formula. Okay, so this was a big event in physics, although it wasn't appreciated for a while, is that how can something that's this large contract to something that's so simple? Okay? So this obviously tells you that this is not the right way to compute the sample. Okay? If this is the answer, this is just wrong. This is just not the way to do it. Okay, so these two things are equal, and this was shown in the 80s, if I'm not mistaken. And this obviously suggests that a different formalism is better suited to compute amplitudes. Of course, it took a couple of decades and Witten to figure out what you have to do here. And he invented this twistor string theory that computes gluon amplitudes as curves in some twistor space. So very complicated formalism that naively doesn't have anything to do with this. But the point is, all of this physics is actually can be explained by a totally different formalism that's much better suited to this job. Okay, and when you express things in this way, you lose some of the properties that were nice here and manifest, but you gain others. So there's a trade-off. You win something, you lose something. Okay, and the question is, what do you want to keep and what do you want to get? Okay, and that's really the difficulty. So from this point, usually a modern, say, amplitudes talk would go in this direction of defining spinners, twistors, and then go to Grossmanians, amplitudohedron. So more and more abstract and complicated objects that basically build on this fact that this amplitude is so simple in the right variables. Okay? So you invent more and more variables that make various things simpler. Okay, now instead I want to go in an orthogonal direction, and I just want to understand this, this mess here. Okay? So to me, this mess is actually very beautiful. And this brings me to something that Mark also mentioned. Can view scattering amplitudes, or I view it as some sort of the tabletop experiment of our century. So anybody with a laptop can just start computing these amplitudes. They get various pieces of data, and then they can start analyzing, look for patterns, try to compute it more efficiently, see what happens in various limits, all sorts of things you can do with if you had your own experiment, right? You can tune anything however way you want. You can compute all of these things. It's open to everybody, right? So it's a totally democratic experiment that anybody can do. And the goal is to compute, gather data, and then find patterns, discover structure, and then go back and so on, right? So it's a never-ending cycle, but you need both of these things to make progress. Okay, now whether you're interested in data to compare to experiment, or you're interested in the mathematics, both of these still go together. Okay, and now why I mentioned this experimental mathematics, it's maybe because I feel like I missed out, like many of us here, we missed out on a great period in particle physics where, you know, every day some new particle would be discovered, and then theorists would go and think about, oh, what theory could this be, which sounded very exciting when I was learning about the field. But I feel that I was lucky enough to experience something like that in grad school. So when I was in grad school, there was this curious empirical observation that people made and shared with me, which was this very recipe that anybody can go home and try it out. So you write down the most general rational function of momenta and polarization vectors, some mass dimension, so it's just some finite function you write down with arbitrary coefficients. Then you impose gauge invariance, and you find the unique answer, okay, which happens to be the Yang-Mills amplitude, depending on the mass dimension. If instead of vectors you go to tensors and a bit higher mass dimension, then you find gravity. Okay, so Yang-Mills and gravity amplitudes are uniquely determined by this recipe. Okay, and in practice, it would look something like this. So here's ansatz for what could be a 4-point amplitude. You write down all of these possible terms, or all possible contractions between these vectors, with all possible poles that are allowed by some assumptions you're making, with some random coefficient. Okay? At 4 points is going to be maybe 60 terms like this. Okay, so you have 60 terms with random coefficients. And then you impose gauge invariance, which simply means that you take some polarization vector and you send it to be its corresponding momentum, and you want it, and the amplitude should vanish. Okay? This is the statement of gauge invariance. And what you find after you do this for enough number of particles, you find that all of these coefficients are equal to each other. Okay? So the result is uniquely fixed up to some number. Okay? And in fact, a weird thing also noticed was that you only need n-1 particles to do this for, which is also weird because you might think, okay, well, let's see. So this is sort of maybe coming from a Lagrangian, and then I want the Lagrangian to be gauge invariant. So we know that the Lagrangian is uniquely fixed by gauge invariance. But here I'm not assuming gauge invariance in everybody. Okay, so and also not all of these terms can come independently from a Lagrangian. Right? There's no Lagrangian you can write down that has all of these different terms. It would be fewer coefficients. And yeah, so the interesting thing here is that here, when you write down this ansatz, you don't assume unitarity, you don't assume factorization, okay, which should be a big constraint. So then we tried proving this, but we were stuck for a long time. But then, incidentally, some other people were doing totally different work, which is interesting, and it's, I guess, good to always look what other people are doing, even if it's not related to what you're doing, because you never know where the inspiration can come from. So around the same time, in this year, Cacciato and Strominger had just found a subleading soft theorem in gravity. Okay, and later, building more on the soft theorems, Hawking, Perry, and Strominger proposed this soft hair proposal, where soft particles could carry black hole information. Okay, so this is totally, this part at least, totally unrelated to what I do in amplitudes. the soft theorem was kind of interesting. So the soft theorem just tells you that if you have an endpoint amplitude and you take one of the particles to be soft, you get some universal behavior like this, where some universal soft factors that depend on the theory multiplying the lower point amplitude. Okay, and up to this year, for gravity, only the leading term was known, whereas in Yang-Mills, people knew the subleading terms. And then Kachadra and Somter found that actually there's more terms, but it stops here. There's leading, subleading, and sub-subleading soft. Okay, so this was a nice result in amplitudes. And somehow this work implanted this idea that soft limits, soft theorems are something that it's somehow important, and it's telling us something about amplitudes. Maybe you can use them as tools in some way. So eventually we realized that you can use soft limits to prove these highly non-trivial observations, because otherwise it's very difficult to even have any idea how do you prove that this complicated linear system equations. So you have 60 coefficients here, right? You get something like maybe 100 equations relating all of these things in a linear way. How do you know that the answer is going to be unique? At least I don't know any sort of obvious mathematical structure that tells you, what to look for. So anyway, we had this idea, and it works like this. So you start with an ansatz, a local ansatz. So you fix all of the singularity structure, but everything else is unfixed. You take a formal soft limit in some momenta, so you get some infinite expansion like this, where here you don't know what these are, it's just random ansatz here. And then you start imposing gauge invariance. So you impose some gauge invariance first in this guy that you're taking soft, and this fixes the first term to look like this. It's going to be the universal soft factor, so you derive it just from here, and then the lower point ansatz. Okay, and now you can use induction. You can use all of the other gauge invariance conditions. You fix this guy to be the lower point amplitude, and then you keep doing this for all of the other guys. So you prove this statement using induction and soft limits. Okay, and like I said, because unitarity is not used at all, this means that unitarity is an automatic consequence of locality and gauge invariance. Okay. And in fact, we can even relax the assumption on locality and just put some very mild assumptions on the singularity structure. So in some sense, both locality and unitarity emerge from gauge invariance, okay, which is totally orthogonal to many different perspectives. First, at the time, obviously, there was this lower the gauge invariance is bad. We should throw it away. It's just complicated things. It's not good for anything. But in this context, it's actually more primitive, more important than all of these things. And of course, the other perspective is that gauge invariance is not even real, right? It's just a mathematical construction we invented, but somehow it knows about locality and unitarity. Okay, so this is quite surprising. So anyway, this was basically just the tip of the iceberg for me. So here's the iceberg. Yes. Well, in what way? It's just a rational function. Okay, good. Yes. So this is actually very absolutely crucial point. So here, the observation, like I said, is that it involves only n-1 conditions to fix it. So you have one guy left, and you use that guy to solve momentum conservation, and you never impose gauge invariance in the guy you eliminate using momentum conservation. Yes. Exactly. Yes. Yeah, that's right. So if this wasn't true and you needed all of them, then the proof wouldn't work and nothing would work. So it's a nice miracle that actually you need, or maybe it's just a hint that maybe it's not so surprising. So this is the iceberg that I've been building on for the last 10 years now or more, I guess. So these are various theories you can consider. In some sense, they are special theories. They have various special properties. It's not a random standard model theory. But these are usually the theories that people in amplitudes like to think about because they have some nice properties. But they range from Yang-Mills to GR, phi cube, sigma models for pions, DBI, which is some nonlinear extension of Maxwell theory, Galileans, which are relevant in cosmology, CHY, which is just a different formalism that I won't discuss, but even this one works. And more recently, even the cosmological wave function can fit into this table. Okay, and here you have the different principles that you can impose. So first, this is what I talked about. You can use gauge invariance to fix Yang-Mills and GR. Okay? And then very similar arguments you can use for the Adler zero for scalar theories. So the Adler zero tells you that when you take a particle to be soft, the amplitude vanishes. Okay, so this was an important condition discovered by Adler, and it applies to these special effective theories. Then something that I'll describe next in a bit more detail, because it's kind of interesting how all of these can be true at the same time. Soft behavior fixes all of these theories, but then so does the UV behavior fixes all of these theories. Okay, so this is something, an interesting tension. Then BCJ relations that I won't describe. And recently, the thing I'll actually focus on by the end of this talk is this new property that was discovered called hidden zeros. Okay? And hidden zeros are special in very many ways. In some sense, they're the simplest thing on this table. It's just kinematical locations where the amplitude just vanishes. Okay, and this is true in various theories. They're very simple to express, and also they were the first we could generalize to loop level. Okay, so all of this table for many years was a big problem that is just at tree level. So you might say, okay, well, yeah, emergent locality and unitarity, but it's just tree level. Yeah. I mean, if you want this to be a universal statement, obviously it has to work at loop level. Okay, and we finally managed to do this. Okay, and in all of these cases, what's interesting is that you never use unitarity. Okay, so in all of these cases, unitarity is a byproduct of these other principles. Okay, and in some cases, so is locality. Okay, and some of these things are proven, some are sort of proven, some are still conjectures. Oh yeah, so it's very interesting that you have all of these principles, that all of them are independent, or at least naively. Actually, I'll show you that they're not independent. But all of these seem independent. All of them constrain the amplitude uniquely. So obviously, you might expect that, okay, maybe they're actually not independent. But you wouldn't like think about how could soft behavior and UV behavior be equivalent in any way. Okay, so now let me describe a bit what I mean by some of those principles, especially this one, which is one of the main ingredients that I'll talk about. This BCFW or UV scaling and recursion. Okay, so this recursion by these people was an absolute revolution in the field. It gave us a recursive way to compute even the most complicated amplitudes in GR or Yang-Mills or others. And it relies on a very simple procedure. So you choose two particles and you shift their momenta by some parameter z and then some null momenta. Okay, so now your function becomes your amplitude becomes a function of this parameter z. And then if the amplitude is unitary, so that means it factorizes on the poles, and it has this scaling or better as you take z to infinity, then there are some simple contour integral arguments you can make to show that the amplitude can be computed recursively from the lower point amplitude. Okay, and this is a incredibly more efficient than any other method people knew to compute amplitudes. Okay, and it applies to Yang-Mills, to GR, and led to a whole like field basically, just using and building on what the recursion actually means. Okay, so this was revolutionary, very practical, very good, but still very mysterious, at least to me. So mystery number one is that some of the factorization channels sort of magically appear. Okay, so for example, the 4-point amplitude in the planar sector is given by two diagrams. Essentially, you have an S channel and a T channel, depending on which particles are coming in and out. And the recursion only has one term, and you can choose to look at just essentially build the whole amplitude from the S channel. Okay, so it's kind of weird. Where do you get the T channel from? Of course, mathematically it works out in some way, but it's still sort of weird that this guy knows about this guy and vice versa. Okay, just conceptually. And the second mystery is what symmetry is behind the UV scale. Okay, so this is a highly non-trivial symmetry of scattering amplitudes. If you try to test it on an amplitude, you need many cancellations between different terms. Everything has to work out. So it's very tight. Okay, so there must be some reason for it. And of course, this symmetry was explored in this paper, which I don't find very illuminating, but it's one explanation we have, at least for Yang-Mills and GR. Okay, But the problem, the mystery runs deeper than just Yang-Mills and GR. Okay, and the scaling works like this and why it's non-trivial. So if you just look at your 4-point amplitude as a function of this deformation, these two terms each have some scaling. You find that in general they'll scale like a power z to 1, but they cancel against each other, and then the overall behavior goes like 1 over z. Okay, so this is the cancellation. So this is really telling you that this part knows about this because of this relation, right? Because of the UV scaling. There's the UV scaling that's relating these two in some non-trivial way. Okay, so then you can ask a natural question if you want to understand these mysteries, which is what sort of functions can have this enhanced scaling? Is it just amplitudes? Can I write down a nice, maybe I want to write down a building block of functions that have enhanced scaling and build amplitudes out of them instead of the BCF recursion? So thinking about this, you naturally are led to this conclusion that with some assumptions like locality or mass dimension, amplitudes are uniquely fixed just by the UV scaling, okay? And this is true in both Yang-Mills and GR. And again, you don't have to use unitarity and you don't have to use the recursion. You just take an ansatz, local ansatz, and demand that it has this UV scaling, it's going to be uniquely fixed. You never have to use the recursion, okay? And then later we found that the same thing happens in some of these scalar theories that I mentioned. Okay, and now this gets weird because for most of these scalars there's no symmetry understanding of the scaling, right? And which is weird because you'd expect the scalar theories to be simpler than looking at the Yang-Mills or GR Lagrangian and trying to figure out a background gauge, something to get the argument. But for scalars, there's no symmetry understanding for the scaling. And in some of these theories, the recursion doesn't even exist. Okay? So you might thought, oh, maybe the scaling is just a secret way to do the recursion. And then it also works for CHY Clausians that I won't discuss. Okay, but so let me just show you how it works in a concrete example. This trace phi cubed theory, which is the planar version of the theory I described in the first few slides. At 4 points, there are these two terms, and then you do this shift, right? You get some z here, some z here, and then at z large, you get this behavior, okay? Which is an improved behavior compared to these individual terms, okay? And then obviously here, if you put random coefficients, this condition would fix the relative coefficient and uniquely fix the amplitude, okay? And the same happens for the sigma model, which is the theory describing massless pions. You write it down. All of these terms have pretty bad behavior, but in the end, everything cancels and you get this behavior. Now, this behavior isn't good enough to do a recursion, okay? So, I mean, you can supplement this information with other stuff and get the recursion going, but just by itself, this is not something you can recurse, okay? But even in this case, the amplitude is fixed, okay? So it's not that it's not secretly the recursion, it's really just the scaling that seems to be fundamental, you know, in all of these cases. Okay, and now let me describe this IR scaling or IR behavior, or maybe it's not just scaling, in general it's behavior. So going back to this work by these people, again, they proposed this soft hair idea where gravitons contain the black hole information. Okay, the soft gravitons contain black hole information. Okay, this is something that is like beyond my understanding, but instead in my understanding, I can ask a more related question, which is how much amplitude information do soft particles carry? Okay, so what do I mean by that? Practically what do I mean? So again, you take some ansatz at endpoints, you take one of the particles soft, you demand that it behaves something like this, where you put in the universal factors, but then here, no other information, okay, just another random ansatz. So you don't put in any amplitude information except exactly what is carried by the soft guy. And then this sort of construction fixes all of the amplitudes in basically, like I said, all of these theories. Okay, so that sort of procedure fixes all of these theories, and I would assume any theory that has a soft theorem is fixed by the soft theorems alone. Okay, and this sounds kind of weird. You know, how is it possible that I just look at the low energy behavior of an amplitude and I'm able to reconstruct it? Okay, it's pretty counterintuitive, but somehow what happens is that the UV information of one particle is contained in the IR information of a different particle. in some non-trivial way, they are maybe entangled. Okay, so all of the information is just contained here. Okay, so now this brings us to a mystery. So how can all of those principles in that table be independent, or are they independent? Right, and in particular, how can both IR and UV constraints independently fix an amplitude? They're opposite regimes of the amplitude, okay, but somehow they independently fix the amplitude. And again, without assuming unitarity or even locality too strongly. So now the big breakthrough came from the hidden zeros. Okay, and now these finally clarify exactly what's the correct relation. So I'll show you in the next slide that this UV scaling that I described is exactly equivalent to hidden zeros. And then this IR scaling, you can immediately see it's some subset of the hidden zero. Okay, so this is the correct relation in some of the theories, not all of them. Okay, and the second thing I'll describe is how can we extend these ideas beyond tree level. Okay, and previously up to last year or 2 years ago, this question extending beyond tree level was just ill-defined. But this surface kinematic technology that appeared finally allows us to ask if integrands can be unique and how can they be fixed. And it turns out that the hidden zeros are enough to fix one-loop integrands in some theories. Okay, so these are the, there's an overview of the results that I'll present. None of this is very technical, so hopefully it's clear, but do stop me at any point. So first, I'll show that hidden zeros are equivalent to what I call a secret BCFW scaling that was previously not noticed. And this applies to any planar scalar theory, which includes something called scaffolded Yang-Mills. So essentially, it applies to Yang-Mills, sigma model, trace phi cube, all of these theories. Okay, then I'll show in this simplest theory how the hidden zeros plus locality uniquely fix the amplitude, so you get unitarity out of it. Then I'll extend all of this to one loop. Okay, so what are the hidden zeros? So this is a new surprising property of scattering amplitudes recently discovered in trace phi cube, sigma model, and Yang-Mills theories by these people 2 years ago. And then later it was extended by using the double copy to other theories. And very recently, even to cosmological wave function by two of the people we have in the audience. So, okay, what are the hidden zeros? Well, it's just very simple. It's just the statement that the amplitudes vanish for particular configurations of external momentum. Okay, so again, going back to the simplest example in trace phi cube theory, it's given just by these two terms. Use momentum conservation to express the second guy like this. And then you notice that if I take this dot product to be zero, these two cancel, so the amplitude vanishes. Okay, and this is the zero of the amplitude in the simplest case. As you go to higher and higher points, of course, the cancellations become a lot more complicated, but it's true to any number of points. And furthermore, near these zeros, the amplitudes factorize. So if I set, you'll see in a second more precisely, but there's a set of these constraints that you have to set to zero. If you set all of them to zero except for one, you get this sort of factorization behavior for the amplitude, where you get the lower point amplitudes. Okay? And I have to stress that this is totally different from the usual factorization due to unitarity. Okay? Usual unitarity, physical unitarity, which implies factorization, is near poles. This is near zeros. It's totally distinct. There's no connection between these two. Okay, and it's quite strange that there's still no physical origin for either the zeros or this factorization behavior, even though there's like possibly the simplest non-trivial property of amplitudes. And it's also surprising that it took so long to discover this property. Okay, so how does uniqueness work? Well, it's the same story just as before. So this was conjectured in the original paper that the hidden zeros uniquely fix these amplitudes with various assumptions you can consider. Okay, and it just works the same way, right? If you start with an ansatz like this, you demand that the amplitude vanishes with this condition, the zero will fix your relative coefficients in this way. Okay, and again, the story goes to any number of points and to some of the more complicated theories. Okay, so now we get into a bit more technical details, but there's nothing very complicated. So let me try to explain all of the ingredients here. So this is part of something that's called surface kinematics, where we describe the kinematics of the problem not in terms of momenta, as we usually do, but in terms of some other variables. Okay? And it's these xij variables, these are called planar variables. They are given by a simple combination of momenta. So you sum all of the momenta from I to j minus 1. And importantly, these variables form a basis. Okay? So we have enough of these variables to eliminate all of the usual momenta, which are the k. Okay, so that's good. So you can write any scalar planar amplitude. You can now write it in terms of these variables. Then it's also useful to define these so-called non-planar variables, the CAJs, which in terms of momenta are the simple combination of two dot products between non-adjacent momenta. So that's why it's called non-planar. And then in terms of the x's, using this relation, you can work out that there's a actually very simple relation between the CAJs and the XIJs. Okay? And you can work out what it is by looking, I'll describe this in a second, but if you just look at one of these rectangles, these are labeled by the various CIJs, and then the vertices are labeled by the various XIJs. And then this relation just tells you that you add the one on top, the one on the bottom, and you subtract the left and the right. Okay, so there's a very simple graphical rule to understand these CIJs. Okay, so that's one part of the ingredients. The second thing is that you can view the XIJ as chords on a kinematic disk. Okay, so you draw this so-called kinematic disk, which is just a disk with some labels on the edge. In this case, corresponding to a 5-point object. So you label 1, 2, 3, 4, 5. Okay, and then you draw these chords. Okay, and you want chords that triangulate this disk. Okay, in this case, you need two chords. You need, say, for example, this one, 1, 3, and 1, 4. And this triangulates the disk. Okay, and it triangulates it because each region has 3 vertices. Okay, so it's like a triangle. This one has, these 3 vertices. This one has 3 vertices. So this is a complete triangulation of the disk. And now if you draw the dual to this disk, so for every chord, I draw a propagator. And for every external edge here, I draw an external leg. I get a dual Feynman diagram that corresponds to this triangulation. Okay, so you can view here, if I choose these two chords, x13 and x14, this corresponds to a Feynman diagram in trace phi cube theory, which is drawn here in blue. Okay, and this is true for any triangulation you draw. So then Feynman diagrams are triangulations of this disk, and then the whole amplitude is the sum over all possible triangulations. Okay, so this is good. So now you have this nice organization in terms of this disk. You look for various triangulations, then you organize the data here. Okay, what's it good for? Because we already knew what all these amplitudes were. Well, this picture makes the hidden zeros manifest. Okay, so now the hidden zeros just tell you that you look at maximal rectangles on this mesh, and you set all of these CIJs in a maximal diamond to 0. Okay, so for example, if you set C13, C14, C15 to 0, in terms of these x's, it implies some linear relations between the x's, the amplitude will vanish. Okay, and it's the same if you choose these 4 CIJs. Okay, so these are the hidden zeros. And of course, this all generalizes to any number of points. Okay, so I should have mentioned, but this is what sort of an amplitude, a 5-point amplitude would look like. Then when you impose these conditions, you get some various linear combinations of the XIJs, which somehow they all cancel. Okay, again, it's pretty non-trivial how it happens. Okay, so now I want to show that actually these hidden zeros are exactly equivalent to a secret non-adjacent BCFW scaling in all theories. Okay, so like I mentioned, these special scalar theories also enjoy some enhanced BCFW scaling that doesn't really have an explanation under non-adjacent shifts. So this is critical. In Yang-Mills and GR and other theories, you can do adjacent shifts. So that means you can consider a shifting 2 adjacent particles, and you can do the whole recursion. Usually the nice way to do the recursion. But you can also choose things to be non-adjacent. And it turns out that for these scalar theories, it's only the non-adjacent shifts that work out. Okay, which is also another mystery. Why for these theories it's only the non-adjacent? Why in this for Yang-Mills and GR it's the adjacent are fine? Okay. And actually, it will turn out that why you don't have adjacent shifts for scalar theories is that the adjacent shifts don't have any corresponding 0 condition associated with them. Okay. So first of all, the first question is, okay, what's shift and what's zero? How do you connect the two? Because it's totally different conditions, right? So it's actually a very simple way to figure out what shift corresponds to what zero. Okay, so for example, you look at any zero, any hidden zero that involves setting a set ofCij's to zero, right? And you look in all of these conditions that you have to set, you'll always find two labels that never show up, right? So for example, this was a zero, right, corresponding to this guy here. It's C13, C14, C15 set to zero. Well, you notice that 2 and 6 never appear, okay? And that will give you exactly the shift you want to do. Or it's true even for like the different types of zeros like this one, right? And here you notice that 1 and 4 don't show up, and on the mesh you can also figure it out. Okay, so there's a connection between any given non-adjacent shift and any zero. Okay, so what's the secret BCFW scaling? Why do I call it secret? So consider this sort of non-adjacent shift on a general rational function. Okay, so a general rational function of this type, where downstairs I have just products of xij's, and upstairs, well, I can have any polynomial in xij, but here it's important that I have just products of xij's. Okay, so this sort of ansatz can include any planar theory you want, Yang-Mills, trace cube, sigma model, it's all of this form. Okay, now when you do this shift, obviously some of the xij's will acquire z dependence, right? Because the xij's depend on the momenta in some way. Some of them will acquire z dependence, some of them won't, depending on exactly how the shift relates to these two labels. And now you group all terms in this ansatz according to the scaling of each individual term. Okay, so first I take the terms that scale the worst, say as power k, zk, I put them here, then I take the next ones here, here, and so on. Okay, and now the claim is the following. If this function satisfies some particular zero, Cij is equal to zero, then these three statements are equivalent. Okay, first, Bn satisfies the zero. This is equivalent to each of these functions actually individually satisfies the zero. And each of these functions has an enhanced BCFW scaling by 1 power. Okay, and all of these statements are equivalent. So maybe I'll skip the proof. It's not very illuminating. It sort of goes, it's all based on a very simple thing you can prove, is that the only linear combinations of xij's that have enhanced scaling are precisely the Cij's. Okay, so that's all you need. Because now it's a very simple logic. If your function satisfies the zero, okay, then it must be at least linear in these variables to vanish under the zero. But if it's linear in these variables, that means it also has enhanced scaling. The enhanced scaling, the leading scaling is carried by this term, right? So then this term must have enhanced scaling. If it has enhanced scaling, that must also be linear in the Cij and so on. And you keep going, and then basically you prove that each of these individual functions has enhanced scaling and satisfies the zero on its own. Okay, and this is called secret BCFW scaling because it's stronger than just scaling of the overall function. Each of these structures within the amplitude each has an enhanced scaling, which also had no obvious physical origin. Okay, so this is the basic proof of this fact. Okay, proving uniqueness is also very easy once you understand the structure, and it's really just comes down to a very simple observation, which is that if you take a residue of your amplitude, you get a lower point amplitude. Okay, at least in this simple theory that I'm talking about. And it sort of looks like this. There's just here it's a sum of diagrams. If you look at the residue on this propagator, you just remove two legs, one leg, and you get a lower point amplitude. Okay, now the same is true if you look at ansatz instead of amplitude. If I assume locality, this relation still holds at the level of an ansatz. Okay, so this is the key point. If I take the residue of a local ansatz, I just get the lower point ansatz. Okay, so there's no hidden connection. It's all, this is the most general n-1 point function. This is the most general n-point function. So then I can use induction basically, right? I can show that on this cut, if you now impose the zeros, actually some of the zeros act as the lower point zeros. So by induction, they fix this residue. All of the residues are fixed. So then the whole thing is fixed up to some number. Okay. So hidden zeros plus locality uniquely fix the amplitude. and unitarity is automatic in this case. Okay, now let me go to loop level. So again, obviously we can compute these things with the Feynman rules. It's nothing complicated. But if you want to get the same sort of statements, it's been a major roadblock for many years, right? Try to extend these uniqueness results beyond tree level. And obviously we want to do this if I want to make this weird claim that the locality and unitarity are emergent. Okay, and like I said, until recently it was just ill-defined because there's no unique integrand. So how can I fix something uniquely if there's no way to, there's nothing unique about it, right? You can always shift the loop momenta, I can do other things, so it's not unique. But finally, these problems were recently elegantly solved by the surface kinematic, which gives us canonical integrands, which is something that's maybe a bit more technical if you don't know about amplitudes, but they have well-defined single loop cuts. So what do I mean by that? Well, here I have, say I look at this sort of function, it has some loop integrations here. I just look at the integrand, okay, it's still some rational function. And I want to understand what happens if I go to sit on one of these poles corresponding to that propagate. Okay? Usually in the tree level case, like I said, if you go to one of these poles, you get the lower point stuff in a nice factorization. Here, usually, you get a higher point tree amplitude, but in the forward limit, right? Because when you cut this loop momenta, the two legs actually have equal momentum. So it's sort of in a weird limit, okay? But in this new language, you actually get the higher point amplitude away from the forward limit, okay? So then you can use all sorts of inductive arguments to prove whatever you want. Okay, so there's some very simple generalizations to get the loop integrand. So instead of the disk, you have to look at the punctured disk, and then you add some y variables, which are all of the variables that connect one of these points to the puncture. And then you allow some more freedom in your x variables. This allows you to keep the external bubbles and tadpoles. So you keep all of the loop structure that otherwise is annoying. But in this case, you need all of the structure, like bubbles and tadpoles, to get everything well defined. Okay, so now again, you can do triangulations of the punctured disk. It looks a bit more complicated, but you can still see the dual diagram is just a Feynman diagram. All of these y variables correspond to loop propagators and so on. Okay, so this is what the 2.1 loop integrand would look like in terms of these variables. And of course, you can go to the actual momentum whenever you want and do the integrals or whatever you want to do. But this is a nice canonical form for the integrand. Okay, and so this is what we did in this paper. And then we also have to define the mesh that works at loop level, because now you have these extra y variables, so it's more complicated, but you can still find the mesh. And now it looks like this. It's like a mountainscape, okay, where again, the vertices are some x's and the squares are somecijs, and this bottom half has all of the y variables arranged in some way. Okay, and then the zero, we find that it actually does generalize to loop level. And now it looks, it's what we call a big mountain. So now you have to set all of the CAJs inside this big mountain to 0. And this gives you a 0 of the one loop integrand. Okay, and you can check again. Okay, so now the conjecture is that these zeros also fit the one loop integrand uniquely, okay, which would be a proof that unitarity emerges even at one loop. Okay, now here's a bit more technical details of why this single loop cut is important, and basically it allows you to run an inductive argument. So when you do a single loop cut, like I said, of an endpoint amplitude, you'll get the n plus 2.3 amplitude, but away from the forward limit. Okay, so you can check in this simple example. I have this 2.1 loop integrand, right? It looks like this. Say I go to this residue of y1 plus, which corresponds to a loop propagator. First, you get something that looks like this. It's just two random variables, but these variables are not related. Okay, so this tells you have enough kinematic space to actually see that this is a 4-point amplitude, but in just after you like relabel some of the things. Okay, and there's a nice way you can see it on the starting from the mountainscape. Whenever you do a cut, this defines some triangular region, and then after you do some relabeling, you can see this corresponds to what I had as the tree level mesh with 2 extra particles. Okay, and there's a picture in terms of these triangulations as well. When you take a cut here, these various curves turn into various tree level chords. Okay, so there's a very nice simple picture. Okay, so then to prove uniqueness, it's very simple. First, you can also show that if you do a loop cut of an ansatz, you get the tree level ansatz. Okay, and then something interesting happens. Now you impose the loop zeros, and you want to see how they act on the residues to use induction, right? And maybe you want to show that they act as three zeros. And then once you do this, probably you're done because you fix all of the residues, so the whole thing is fixed. Okay, but the story is actually very interesting, and it gives an origin of all of the different types of hidden zeros at tree level. Okay, so here I said that if you look on the cut, on the residue, right, this defines some triangular region. Then I said the zero is this mountain shape. And then the superposition, or I mean the overlap between these two triangles gives rise to different maximal diamonds. Okay, in this case, it gives this guy that corresponds to this guy. And then this overlap gives you the other zero and so on. Okay, so in this picture, the three zeros are unified at loop level. Okay, at loop level, there's only one type of zero. It's just this mountain. At tree level, it was sort of weird that you have the different shapes of zeros. It's not obvious why they come from, why it's so different. But at loop level, they're all the same type. Okay, so this is a nice understanding. And you get the different things at tree level depending on where you cut the loop propagator. Okay, so then the proof just works out. You fix all of the residues by induction, and you're done, right? And then you can claim that unitarity is a consequence of locality and hidden zeros even beyond tree level, okay, at least for this theory. Okay, now there's a conjecture you can try out that's highly non-trivial that this works even if you don't assume locality. Okay, the number of terms in the ansatz grows very fast. At 4 points, it's almost impossible to do on a normal laptop. And you have just a linear number of constraints, and somehow you fix all of these factorially growing number of terms. Okay, so it's highly non-trivial. And the problem is if you don't have locality, you cannot use this, right? Because then it's all sort of garbage. You cannot induct very easily. Okay, so I'm almost done. Actually, how many minutes do I have? Oh, okay. Okay, I'm almost done. Yeah, so so we also show that at one loop level, we also have a new type of factorizing behavior. So I described this sort of factorizing behavior at tree level, where you are near a zero. In this case, it's sort of similar, right? You had the zero with the mountain for a zero, but you pick one guy here that you don't set to zero, and the amplitude will factorize in some way, which is very similar to a forward limit, but it's not really, so it's kind of strange. And then the conjecture is that the sigma model is also fixed by this property at loop level. Okay, so just to summarize, I showed that hidden zeros are totally equivalent to a secret BCFW scaling. I proved that locality and hidden zeros give you unique amplitudes, so unitarity follows as a consequence at both tree and one loop. And then the conjecture you can try out numerically is that this holds even without assuming locality. But it's, I've been trying for a year to prove this, still not success, but I can try some more. So just some very quick open problems. It's, like I said, prove this without assuming locality. Then there are other zeros you can find. We don't know what the origin of these things is. You can try to prove the same thing for Yang-Mills. Big question is what happens to color kinematics in this new language? And then the big question is, can you prove this even to higher order loops? Okay, and then you might be able to claim that zeros imply locality and unitarity maybe to all orders in perturbation. So that's it. Thank you.
Thank you for nice talk. Are there any questions?
Where what software is being used by the community? On page 9, you said one can compute using
Yes.
computers. What is being used?
Just Mathematica. I mean, this is a 2-line code you can write down in Mathematica or your favorite programming to compute this. There's very simple rules to put everything together.
So in your community, it's Mathematica that is being used.
Yeah, just Mathematica. There's nothing fancy. I mean, people use very fancy things, but I don't.
So maybe we go to the last slide. So proof for Yang-Mills uniqueness from zeros relations to gauge invariance.
Yes.
So maybe you can speak about who's working on this.
Well, I would like to work on it, but I don't have time. So you can try the same thing. So Yang-Mills ansatz is uniquely fixed by the hidden zeros. So then the question is, we know that Yang-Mills is fixed by gauge events and the other properties. So can you, is it going to be the case that the hidden zeros are just equivalent to gauge invariance? That's a good possibility, but yeah.
Progress has been made on this.
I checked that it's true, but that's it. And it's a bit more difficult than the simple theory I showed you because Yang-Mills has numerators. So now it's a bit more complicated, but
Other people who have been working on this?
I don't think anybody. I don't think anybody's working on this. So you can try.
I expect it's more difficult than.
Yeah, because now you have complicated numerators in the ansatz. So originally, all of the ansatz has just poles stuff in the denominator. Now Yang-Mills has complicated numerators. So the whole thing is going to be more complicated proof. Maybe there's some way to do it.
Just the computational observation.
Well, there has to be an underlying principle, but so far this is observational physics. I mean, you just do things, you observe it, and you try to explain it in some way. In this case, I don't think any of the things, I mean, this equivalence, this equivalence doesn't really explain the physics of either of these properties. I mean, they're just equivalent, so now you have, if you understand one, you understand the other. But physically, we don't know why this is true. We know, I mean, you can prove it's true, but and you observe it, but we don't know why, where it's coming from.
What about the reverse?
Oh, well, yes, yeah, but I mean, then you usually have, in these theories, if you have unitarity, then you define the whole thing. There's no freedom to do anything. So in this case, unitarity is just gives you everything. There's nothing left to do, and then you obviously check that the amplitude does have the zeros.
I'm going to try to answer your question, even though I just have a vague idea. But my impression is that, well, there has been a lot of evidence that the gravitational and gauge theory amplitudes are related at the integral level, right? So this is a color kinematics duality. And so if you want to run this program of bootstrapping from the soft limits, technically you have more information in the gravity amplitude because you have all kinds of sort of non-ordered poles. Right? So you have not only the planar poles, but the non-planar ones too. So if it's true that gravitational and tree-level amplitude, gravitational and gauge theory amplitudes are related, at least at tree level, right? Then there must be some information that's hidden in the planar amplitudes, which is, I think, exactly this hidden zeros. And I think you can see this in one pedestrian way from the BCJ relations. If you just look at factorization of the other orderings in their other planar limits, there's an implication for the planar amplitude, which is exactly this zero. So that's kind of my impression from these results. That somehow the sort of gravitational or non-order or non-planar theories have some more information that is hidden in the planar case.
Yes, but I don't know how it helps you. I mean, yes, obviously, if you write GR as the double copy, then each ingredient will have zeros. But I don't know exactly how, if this is, I'm not sure what sort of information this gives you.
Well, we don't know what the zeros of the gravitational amplitude are exactly. But we know that it factorizes in non-planar poles, not only the planar ones. If you fix an ordering, then there will be more information in the non-planar case.